we've got 3 ink cartridges that are going to be drawn from a box of 12, 9 of which are, so here's a box of 12 ink cartridges. There's 12 of them all together, and we're going to draw 3. So R is equal to 3. And in this box, there's 9 with ink, so 9I, and 3 without ink, I prime for not ink. And what we're going to do is draw these in succession, one after another. And what we're looking for here is this, the probability that the first 2 cartridges have ink and the third one does not. Let's write that. I'm looking for the probability that, I gotta have some kind of notation. So how about ink in the first? The subscript just means which item I'm looking at, the first one. So ink in the first, and I want ink in the second, and I want no ink, I prime, in the third. So these are ands, and they're not independent events, right? Because we are drawing without replacement. So if you take a cartridge out, it affects what happens into the sample space. The sample space changes, it gets smaller. So this is just going to be a multiplication here. What's the probability of getting an ink on the first times the probability of an ink on the second times the probability of an ink on the third? And let's see, the probability of an ink on the first, well, there's 9 cartridges with ink, and 12 of them all together. So this is going to be ink on the first, 9 with ink, 12 all together, 9 twelfths times. Now you've taken that cartridge out, so there's only 11 left, and you took one with ink out, so there's only 8 of those left. Now there's only 10 cartridges left, and now you want no ink. Right, so we want, actually this is no ink in this one. So we want no ink, and there are 3 of them with no ink. So we're going to get 9 twelfths times 8 elevenths times 3 tenths. And when I did that on my little calculator, I'm getting this to be 0.1636. So this type of an event will happen, if we had to say, maybe about 16% of the time. Now, we've got a TV set that contains 5 circuit boards of type A. You know what, let's see if we can summarize this. What we have is we've got 5 A-type boards, 4 B-type boards, and 3 C-type boards. So all together in here, we're going to have 12 boards. And now, we're given that the boards are independent. That means if, one of them fails, it has no effect on the other. So what's the probability that no circuit board fails? All right, so we have no circuit boards failing here. So what we're going to have is, we got 12 circuit boards all together. So we're going to have no failures for A. So what we want is this. We want no failures for A. Now, the probability of A failing is 0.03. So the probability that A does not fail is 0.97. The probability that B does not fail is 0.96. And the probability that C does not fail is 0.95. Now what we want here is no failures for A. So I want no A's failing. So what I want is this, no A's fail, and no B's fail, and no C's fail. Well, what about this right here? Now, these are independent events, so what I want is no A's failing times probability of no B's failing times the probability of no C's failing. All right, now, no A's failing. The first, second, third, and fourth, and fifth can't fail. So we're going to have no fails, 0.97, and there's 5 of those. Times, now this is no B's failing. The probability of B not failing is 9.6, and we've got 4 of those. And then C failing, not failing, is 9.5, and there's 3 of those. right? Do you see where that's coming from? No fails for A. So the first one doesn't fail, and the second, and the third, and the fourth, and the fifth. So there's 5 of those 9 sevens being multiplied. And my calculator shows this is a 0.6253. So I am getting this to be 0.6253.